Hello, I welcome you all in this presentation related with the subject materials processing fundamentals and practical. And we are talking about the practical and lab demonstrations related with the course material processing. In this particular presentation, I will be talking about the three different methods of controlling the microstructure in order to realize the desired mechanical properties and other characteristics. These methods include like heat treatment, TIG remelting and the friction stir processing, and thereafter we will try to see like how image analysis can be useful in assessing the suitability, feasibility and effectiveness of these methods to control the microstructure. So, as far as learning objectives are concerned, to learn about the control of microstructure using three approaches: friction stir processing. This is the solid state process which involves severe plastic deformation of the metal. So, basically the dynamic recrystallization of the material happens, which causes significant refinement as well as sometimes due to the thermal cycle imposed even metallurgical transformation, and the metallurgical phase transformations also take place apart from the grain refinement. Okay, the phase transformations also occur. Then heat treatment, which basically involves the controlled heating, soaking and cooling cycles in order to realize the desired microstructure and phases, so that the control over the mechanical properties. So, mechanical properties can be realized through the appropriate control of the microstructure. TIG remelting is one approach which is especially useful for the castings. Why? Because casting usually result very coarse grain structure due to the slow cooling rate. Also, it suffers from the common defects like porosity and inclusions. So, and this is happening due to the relatively low cooling rate which is experienced by the molten metal during the solidification as far as the coarse grain structure is concerned. So, when we apply a controlled heat for melting the near surface layers with the help of TIG, the melting takes place. Impurities in form of inclusions, they will be coming up to the surface, and the porosities and all that will be collapsed. So, what will be happening after the solidification? During the solidification, since the cooling rate experienced by the molten metal which is produced through the TIG arc, that is higher. So, higher cooling rate experienced by the molten metal during the solidification results in the refined structure of the grain. Even if it is the transformation hardening metal, then this kind of the remelting can also produce the hard constituents at the surface layer. So, the TIG remelting does two things. One, it removes the defects, it eliminates the defects from the near surface layers which is remelted, and it refines the structure, refines the grain structure, and even sometimes the new phases are also formed due to the rapid cooling that will be encountered by the metal due to the TIG remelting. Okay. So, we will try to talk about like how effective these techniques are for controlling the microstructure, and also we will try to see that how image analysis, especially the microstructure analysis using the micrograph, can be performed using one software like say the image analyzing software, so that we can check the effectiveness of these methods in altering the microstructure and so realizing the desired mechanical properties. What we need, they say castings of aluminum alloys which are usually coarse. So, we want improvement in properties say through the heat treatment, through the FSP or through the TIG remelting. Okay. So, when this is applied in the casting, for what we need for heat treatment, we need a suitable heat treatment furnace. For FSP, we need FSW machine so that the friction stir processing can be performed, and for the TIG remelting, we need the TIG machine so that the arc heat can be applied in controlled way at the near surface layers. Also, we need to characterization tools and the machines so to see that how effectively the microstructure has been regulated and controlled. So, that is done with the help of suitable microscopes, and also the suitable image analyzing softwares can be used. Other mechanical properties like hardness and tensile properties, all those are very standard one, and when the samples are subjected to this kind of control over the microstructure. These can be used to assess how far the mechanical properties are getting affected due to application of these techniques. For characterization, for say sample preparation, what we need? Grinding, polishing, then etching for optical microscopy. So, this is a typical polishing machine, and then microscope is to be used for optical microscopy to capture the microstructure of the sample in as cast condition, and later on when it is processed through the FSP heat treatment or TIG remelting. So, we need optical microscope, and to check the effectiveness of the microstructural control, we need to check the hardness of the processed samples. So, a suitable hardness test method can be applied on the components in as cast condition as well as after that of processing. This is a typical Vickers hardness testing system. So, as far as the heat treatment is concerned, we will try to see that how the solutionizing, you see, in the heat treatment of cast aluminum, silicon, magnesium alloys, usually the T6 heat treatment is done, which involves solutionizing, then quenching and aging. So, in quenching we have two aspects, one is the quenching solutionizing temperature and another is the time. So, how the solutionizing temperature affects the microstructure and mechanical properties while maintaining other two steps like the quenching and aging same. So, in this particular kind of the case, we will be investigating how the solutionizing temperature affects the microstructure and the mechanical properties of cast aluminum, silicon, magnesium alloys. So, three types of the cast aluminum silicon alloys will be taken to see the effectiveness of the solutionizing temperature. As far as the materials and methods are concerned, we have to use the suitable master alloys, pure aluminum and master alloy of aluminum, magnesium, silicon and and aluminum silicon master alloys, and in proper proportions these are mixed and then they are melted in the suitable graphite crucible with the help of furnace, and then the casting is made using the metallic mold of this size. And three types of the cast alloys were made, say like say aluminum 8% silicon, aluminum 12% silicon and 16% silicon, one of hypoeutectic and another is hypereutectic and one is eutectic. Okay. Then hypoeutectic and eutectic alloys were modified with the help of the 0.015 strontium using aluminum 10% strontium master alloy, and hypereutectic alloy for refining the primary silicon particles 0.01% phosphorus was added. These alloys in S cast condition later on subjected to the heat treatment, T6 heat treatment, involving the solutionizing, quenching and aging. So, solutionizing was done at three different temperatures, say 450, 480, 51 and 550 degrees centigrade for 8 hours. So, these four temperatures for solutionizing were used to investigate how far solutionizing heat treatment affects the microstructure and mechanical properties. After solutionizing, quenching was done in water at say room temperature of 30 degrees centigrade, followed by artificial aging at 170 degrees centigrade for 12 hours. Now, we will see how this heat treatment affects the microstructure and mechanical properties. So, to study the effect of the solutionizing temperature, we have to see what is the microstructure at room temperature in as cast condition, and thereafter how the structure gets modified when the alloy is subjected to the T6 heat treatment. So, as cast structure of aluminum 8% silicon 0.3% Mg, what it shows mainly alpha aluminum with little amount of the eutectic in the matrix. Okay. This is the, but when the solutionizing is done at 510 degrees centigrade, what it shows, the eutectic silicon is broken down and still although aluminum still remains little bit in the dendritic form, and whatever the silicon is there, that is broken down and remains at the grain boundaries. And but when the solutionizing is done at 550 degrees centigrade, the as cast structure is completely broken down and very fine eutectic silicon particles are observed. Okay. And the same thing we can see in case of the aluminum 12% silicon, as cast structure is showing the alpha aluminum and the eutectic silicon. Eutectic silicon is broken down at 510 degrees centigrade on solutionizing, followed by quenching and the aging, and the complete and more fine refined structure is produced when the solutionizing is done at 500 degrees centigrade, 550 degrees centigrade. And the same is also like primary silicon particles and eutectic silicon. and eutectic is coupled with the alpha aluminum can be seen in the hyper eutectic aluminum silicon alloy. The aluminum eutectic silicon is especially broken down into in form of fine particles in matrix of the aluminum, and the primary silicon particles still remains in the same way. But when when the solutionizing is done at 500 degrees centigrade, we can see that the all S cast dendritic structure is completely broken, and a very fine eutectic silicon and the primary silicon particles are found. What it suggests that solutionizing at a higher temperature helps in refining and breaking down the complete S cast structure, while this kind of the refinement and breaking down of the S cast structure is somewhat limited when the low solutionizing temperature is used, followed by quenching and aging. So, that is what we will also be reflecting when we use the lesser temperature, the hardness is less. On increasing the temperature, increases the hardness. So, that indicates that increasing solutionizing temperature increases the effectiveness of the T6 heat treatment. Now, we will see that how the friction stir processing helps in controlling the microstructure. So, here if we see, this is a surface modification approach where say this is the cast alloy. So, using these simple the FSW tool, the tool rotating tool is plunged, then it is traversed. Okay. So, this will be modifying the surface layers up to certain depth. This is not a joining, this is just controlled surface layer plastic deformation for refining the grain structure. So, in S-cast condition, we have coarse structures, particles of silicon and the silicon needles, okay. And these coarse particles in form of needles, these act as a stress razor and thereby these reduce the strength. So, if we do the FSP of especially cast aluminum silicon alloys or hyper eutectic cast aluminum silicon alloys, then the significant refinement of eutectic silicon and the primary silicon particles will be taking place due to the FSP, because of the severe plastic deformation, all these will be broken down, and this in turn helps in significant improvement in the strength and the ductility. So, what FSP does is that refines the all constituents, eliminates the pores and defects because of the consolidation, and it work hardens the surface layers, and in case of the TH metals like steels, even transformation hardening can be observed, and also it helps in a more improved distribution of the micro constituents and alloying elements. So, here if we see the S-cast structure is like this, showing the coarse grains, okay, and say in the plate when we use the FSP one pass, then another pass, then another pass, then multiple overlapping passes are applied. So, this is the case where the multiple overlapping passes have been used for modifying this larger area of the surface. So, this is the kind of the base metal, and when it is refined, like FSP zone is completely refined, this is the unprocessed zone, this is the processed zone. And when the processed zone is observed, then we will see the significant refinement in the grain structure takes place. So, if we try to see the variation in properties due to the FSP, so as far as the FSP is because of the improved hardness and surface characteristics and refinement of the grain structure of the steel, what we get, the unprocessed material shows the the erosion rate the lower, and the processed material, unprocessed material shows the higher erosion rate, and the FSP reduces the erosion rate significantly. And if we check the hardness variation, near surface layers shows the significant increase in hardness due to the grain refinement as well as the transformation hardening related favorable phase transformation. Okay. So, what we see, the near surface layers are significantly harder as compared to those which are away from the surface. Unprocessed zone is showing significantly, unprocessed steel shows a significantly lower hardness, while after processing we find a significant increase in hardness, and this is attributed to the improvement in the erosion resistance of the steel if it is used. So, FSP of the steel helps in increasing the hardness and in improving the erosion resistance. If we talk of the FSP of the aluminum silicon alloys, then what we will see, this is the hyper eutectic aluminum silicon alloys showing the primary silicon. Okay, all these are primary silicon particles in the eutectic matrix. So, these primary silicon particles, when these are subjected to, then FSP is subjected to the cast aluminum silicon alloys, then these big primary silicon particles are broken down into the fine particles, and these fine particles we can see are produced at the different friction ester processing speeds, let us say 26 mm per minute, 40 mm per minute and 60 mm per minute. So, what we see, the refinement of the grain structure is in general that is achieved after the FSP of the cast hypereutectic aluminum silicon alloys, and that is what we can see here with regard to the effect of this is S cast alloy. And when we do the FSP using the different sets of the RPM, like say RPM 664 and the traverse speed of 26, 40 and the 60. So, this is the optical microscopy and this is the scanning electron microscopy, that is the only difference. So, when we try to study the transverse, the section of the FS speed zone, then what we see, the FS speed zone shows that there is, this is the hardness of the location of the hardness. So, this is showing the, this is the zone where the hardness was measured. So, location A is showing the location where hardness of the FS speed cast aluminum silicon alloys was measured for the different conditions. Okay. So, what it shows that FSP brings in the significant uniformity and little increase in the hardness also after the FSP. Okay. So, A is for the S cast alloy, what it shows significantly lower hardness as compared to that of the FSP. FSP increases the hardness because of the more improved the distribution of the silicon particles. So, FSP increases the ultimate tensile strength also, that is what we can see from this, the diagram, where you can see the base metal is significantly weaker in terms of the strength as well as ductility. But when the FSP is performed, there is a significant increase in the tensile strength as well as ductility for all these conditions. So, in general FSP is increasing the tensile strength by 1.26 to 1.3 times. It increases the elongation significantly from about 2 to 8%, and it increases the micro hardness also. An increase in welding speed increases the microstructure, that is the in general observation. We know that the cast aluminum silicon alloys result in a very coarse grain structure due to the low cooling rate, and also it causes the defects like porosity and inclusion. So, if we using the TIG arc, we realize that the melting of the alloy surface up to certain depth, then what it will be causing? It will be eliminating the defects and also refining the grain structure after the solidification due to the rapid cooling rate. Okay, that is the logic and the idea behind the TIG remelting for improving the surface characteristics by refining the microstructure. So, we will take the cast aluminum silicon alloys like say aluminum 0.8% magnesium and 0.6% silicon. Okay. And the remelting was carried out using the suitable pulse GTAW using a peak current of the 250 ampere and the background current of the 125 ampere using pulse frequency 25 to 50 hertz at a duty cycle of the 40 and 50, and the voltage was like 12 volt. Okay. So, here now we will see as cast aluminum magnesium alloy, what it shows, very coarse grain structure. You can see these grains are extremely coarse. Okay. And when we perform the TIG remelting, say this is the surface. Okay. And here we have got very coarse structure like this. So, and we are melting up to certain depth. So, whatever depth is melted, that zone will be refined certainly, but all those zones which experience the heat, they will get the coarse end. So, the coarse grained HZ is produced. That is what we see. This is the S cast alloy, that is fine, but the zone which is affected by the heat, that is the heat affected zone, and then there will be a zone which will be partially melted. So, this zone that corresponds to the fusion boundary, this is the fusion boundary zone, where you can see there will be part which will be melting and there part which will be affected by the heat. Okay. And the third zone is the fusion zone. So, fusion zone, this is the fusion zone, this is the fusion boundary. Okay, this is the heat affected zone and this is the base metal, okay, in as cast condition. So if we compare this structure, this is the zone which has melted and experienced the rapid cooling rate. So this has been refined significantly, and this kind of refinement improves the structure, improves the properties, improves the tensile strength, etc.
So this one is our stereotype microscope, and this one is our lens is here, and this is the place where we keep the sample. This is our focusing knob. By adjusting it, it will focus. And this one is our magnification power. It has a total six magnification level 0.67x, 1, 2, 3, 4, and 5. And each one denotes the multiple of 10. 0.67x means it's the magnification power of 6.7x. 1x means 10x, 2, 20x, like this. So currently we are measuring the sample. We are taking the images at 6.7x. Now this stereotype microscope is attached to our system. So we are seeing uh, we are looking the image in our software, that is VUE 2014. Now opening the camera. Now as we are just, it's almost focused, but we are trying to get more clear image by focusing it through the focusing knob. Okay, so now we can see the clear image. And now we put a scale bar for before putting the scale bar, we need to choose the magnification scale in the system also, that is 6.7x. So now we're putting a scale bar magnification scale, and we put it. Now this is our scale bar, that is 1 mm. As scale bar means this sample denoted this one distance is of 1 mm distance. So this is showing the scale bar. Now this is our image. From where we can see there are several zones. Just magnify in this area. You see that there are different kind of zone is there. Like this one is our base metal. This one is our stud material through the tool. There you can see the clearly pin is rotating in this section only. Okay. Now just adjacent to this, you can see slightly, if we see clearly, there is a little bit different zone, different kind of zone we can see here. Like this one is TMA zone, TMA Z zone, and just close to it where we can see the some change in colors or heat that is just come from the heat affected zone. So that we can see from here. Now next is scaling the different length. See, this one is our horizontal scaling. We are choosing it and measuring the what is the horizontal length of this different section. This one we measure the upper shoulder regions. This one is 16.03 mm approx. So and our shoulder diameter is already 16 mm. So it's coming means whatever we have used the tool shoulder dia, that is it's coming exact almost same 16 mm. So likewise also we can measure the pin diameter of mean, that is from one end of this to another end. That is 6 mm around approximately. And likewise we can measure the vertical distance, that how much pin length is. We can see here from starting point to the end of the point. You can see our pin length is around 6.04 mm. Likewise, we can measure our plate thickness also from one end of the plate to the another end of plate. That is, you can see 6.33 mm. And our plate thickness originally, initially our plate thickness is 6.3 mm, and after measuring from this microscope, it's coming 6.33. Means our result are in line with the observed result. So next thing is we can save the data if we want with this length and dimensioning. So likewise, there are two different mode. We can change the color and setting. So this one is default mode, and next one AWB mode, which will show our black and white images. So now we can save it. like in this way by giving any name, or we can save in default mode where we can see the whatever the actual color means in somewhat colored mode we can save also. That's on this way we get one more thing. There's two option. One node is here. If we press it, we can see the such things in our eyepiece. Uh, and if we press this, this is our eyepiece. We can directly see the image from the camera, but we can't take it. No, we can't take the data in our soft copy. But if we need it to catch, then we need to press this button, and we can get the image in system.
Now we'll see that how the image analysis can be performed and what are the different objectives that can be realized through this analysis. So, an image analysis, so basically objective behind this is to understand the capabilities and significance of the image analysis of the micro or macro photographs of the joints or the cast surfaces or the formed surfaces, whatever it is. So, here we will try to learn the methodology of image analysis of the macro and micro photographs. Okay. And how it will help in identifying the size and shape of the various phases and defects. It will help in determining the area fraction, circularity and aspect ratio, the number of grains, and also image processing means it helps in refining and improving the quality of the images. Now we will see the procedure of the image analysis for micrographs and macrographs. So, first of all we have to use one image analysis software, and we will be using ImageJ, one of the open source software. So, this is the ImageJ exe file. So, that I will be clicking. So, this is the menu of the ImageJ software. So, it has file first. No? So, what we have to do? We have to click on the file and open the file of the image to be analyzed. Okay, say this is the image to be analyzed, so it will be opened like. Yeah, so this is the image which has been opened, and if we see in this image there is one scale, a scale of this much length of right, and there is like SES defect, blisters, casting surface, and the micro constituents. So, now if you want to do the analysis of the microstructure, of the defect size, of the proportion of this defect, etc., everything can be done. So, what we have to do first, we have to check the what type of the image it is. So, every image is to be converted into the 8-bit type of the image. So, I will go into the file, into the menu and see image, type of image we will check, and if it is of any other type of the image, then it will be converted into the 8-bit. So, you will just click on 8-bit. This is the type of image. Okay. So, nothing to worry, everything is fine, no conversion is needed in this particular case. And then now we'll adjust the threshold. Okay, adjust the threshold of the image. So, this is the threshold, this will be adjusted. So, it is showing everything dark one. So, there are two slide bars, these will be adjusted this and that as per the kind of the face or the area to be analyzed. Okay, like this. So, so this kind of the adjustment we can continue to do until we find that the desired phases to be analyzed have been selected. Say there is no phase selected, and now you see the alpha aluminum is getting selected like this. Okay. So, this kind of the adjustment we can continue to do. The second one, say in this case alpha aluminum has been selected, and otherwise also we can do in different way like this. So, what we will be doing in that case, it will be like the defect has been selected now, or the gas hole has been selected, and we can keep on adjusting this. Okay, like this. So, the area will be selected like this of the periphery of the defect has been selected. Now, we can continue to adjust in such a way that our matrix is selected. Okay, like this. So, our alpha aluminum is not selected, but the eutectic matrix of the Ly is selected like this. All right. So we can continue to adjust as per our need until we are satisfied with particular thing, right? So this is one aspect. Like threshold is very important aspect as far as the image analysis is concerned. Say this is what initially we are selecting the alpha aluminum, right? Now the next thing is also after adjusting the threshold as per the requirement, what we do, we have to set the scale. So what we do, we know that this is the length of a particular, this is the line of particular length. Okay, this is micron marker. So we draw a line of this known length of 0.5 and we'll try to analyze, measure it, what it is. So this is of 177 pixel. This is this measures in terms of the pixels. So this is the length. Okay. So we'll just keep it as it is and now we'll set the scale. Okay. So 177 is that length and how what is the known distance? Known distance here is 0.5. Okay, 0.5 unit is how much? It is in 0.5 mm. Like so, our scale is set now. Right now, we have to now we can select the area to be analyzed. So these are the various options regarding the area choice. It can be rectangular, it can be circular, or any regular shape also. All right. So now here, say we consider the rectangular shape like this. Okay. So this is the area that will be analyzed because we want to say quantify the area fraction average size of the alpha aluminum. Okay. So now we'll go for the set measurement. In the measurements, what are the things that we want to analyze like area fraction area or the perimeter or circularity, etc. Okay. So this is already set. Now what we want, now we'll go for analysis. So in analysis, if you want to quantify whatever is the red highlighted zone that will be analyzed. If you want to know very fine size particles should not be analyzed, then we can select like very small size particles are neglected, only large size particles are kept for the analysis. And these are options, this will indicate like what will be at, what is being analyzed that will be highlighted. So if you put the mask, the area being analyzed will be highlighted like this. Okay. Now we'll start the we'll select. So this is our analysis. What it is showing, threshold is in this range. Number of particles which are being taken into the analysis are 20. The total area is this much. Average size is say 6.006 mm and area fraction of the alpha aluminum is 36%. All right. So this is the one analysis. We can choose the area in different way. Like we can use the circular thing like this. All right. Circular area also can be selected and we can go for analysis again. Okay. Analyze the things and it go like this. So here, since we have not limited the small size or excluded the small size particles, so now it is given 214 and average size is say 4.81 at 10 to the power minus 4. Okay, this is how it will be given. Area fraction is 39%. So based on our choice, we can select the suitable area by using these commands. All right. Now we can go for adjusting the threshold again as per our need. Now, if we want to analyze the defect size, okay, defect area. So say where is our defect? Defect. This is the defect, right? So what we can do, we can select the area. Okay, say this is the area which is being selected, right? This area is being selected. Okay, so this is the total area, right? And the highlighted zone. So what it will see, all these are the defects. So their area and average size so will be counted. So one is major and then other few are smaller defects. So now if you go for analysis of this one, what will be getting? We can also limit here like 0.001 is the smallest one. So now if we go for analysis, fine defects have been eliminated and the large have been kept. And how many are these? These are like say 2 defects. total area is this much and average size of the defect is this, and area fraction is say 15.9. Okay. And similarly, what we can do now, we can go for the analysis of um, the matrix. Okay. Like say this is the area. Okay. Selected, and we can go for its analysis. What it will give us? The matrix proportion and the it's a size. So again, if you go for all particles, so then all matrix that is of the eutectic, that will be selected, and its fraction is say 51.9. This is the average size, and these are the number of particles. Okay. So what it can give: number of particles, average size, area fraction, circularity. For our the need, it gives the number of the results. Now, we'll summarize this presentation. In this presentation, basically, I have talked about the three different techniques which are used for controlling the microstructure, namely the heat treatment, the frictionist processing, and TIG melting. And we have also seen like how to perform the image analysis to see the effectiveness of the methods which are used for controlling the microstructure. Thank you for your attention.